Good morning and welcome to Computer Vision on iOS, Detecting Logos. I'm Paul Himes, a software developer at Livefront and the lead iOS engineer on the Box Tops for Education app for General Mills. Today I'm going to talk about how we used computer vision to solve a challenging user education problem in the newest version of the Box Tops app. We'll go step by step through our problem-solving process and learn about some of the tools and techniques we used along the way. Let's start with some background. The long-running Box Tops for Education program allows you to earn money for your school when you buy participating products. And last summer, General Mills relaunched the program with a digital twist. Instead of clipping out rectangular cardboard logos from the tops of product packages, users can now scan their grocery receipts with a mobile app to earn money for their schools. But there was one little problem. For years, customers had been clipping out these coupons. So it was understandable when people tried to scan these instead of their receipts. Now the app would try its hardest to find receipt data, but since there was none to be found, there really wasn't anything it could do. This led to confusing scanning failures and a user experience that was not great. So let's try that again, and this time imagine what the user should see when they scan a box top instead of a receipt. Maybe a helpful error message. But how can we teach our app to know if the user is scanning a box top? One common approach is to use machine learning, or more specifically, a neural network trained to recognize if and where a box top is located in an image. After all, computers can detect dogs and cats. Why not box tops? So, how would we do this? First, we need to collect a lot of pictures of box tops. About 100,000 should do it. Next, we need to annotate the images. This means manually going through and painstakingly marking the corners of the box top logos within the images. Then we feed this huge collection of images and annotation data into a machine learning model. This could take some time, so we'll come back tomorrow to see how it went. Then finally, we can test our model to see if it does indeed detect box tops. This might work pretty well for some of the time, but when it fails, we won't really know why. Now, as you've probably guessed, we didn't really have the time or the resources to take this approach. So we began to look for an easier way. Luckily, when your problem involves analyzing or detecting content within images on iOS, there's a great first place to look. It's called the Vision Framework. It's a collection of tools and pre-built algorithms for detecting common items in images, such as barcodes, text, faces, and objects. It's optimized to be efficient and run at high speed. Unfortunately, there's no built-in algorithm for detecting a specific logo image, like a box top, within a larger image. But lucky for us, the box top logo is a rectangle. The following is a demonstration of the unfiltered stream of rectangles detected in a video. And just a quick warning, if any viewers have photosensitivity to strobe effects, this portion of the presentation includes some quickly flashing shapes. And here it is. Now, this is far too many rectangles to analyze for every frame of the video. What you're seeing here is about 300 rectangles every second. And many of them aren't even close to the expected size of a box top logo. But the rectangle detector makes it easy to filter this stream to only return rectangles that are of the size and shape that we're interested in. The minimum aspect ratio controls how long a rectangle can be. The maximum aspect ratio controls how square a rectangle can be. We chose these values because they roughly match the expected aspect ratio of a box top logo. Quadrature tolerance controls how slanted a rectangle can be. Maximum observations controls the number of rectangles to detect in a single video frame. Minimum confidence is the likelihood that a result actually is a rectangle. And finally, the minimum size controls how large a rectangle has to be before it is detected. Now let's look at the video stream again, with these filters in place. There are still a large number of rectangles detected, but there are far fewer. And the remaining rectangles will all be roughly the size and shape that we expect to see if the user tries to scan a box top. But how can we tell if one of these rectangles actually contains a box top logo? We need a way to analyze these rectangular portions of the image, and since the user may be holding the phone or product package at an angle, the first thing we need to do is straighten out these rectangles. For that, we'll turn to another iOS tool called Core Image. Core Image is a general-purpose image processing library. Most iOS apps that let you apply filters to images are based on Core Image. But for our purposes, we'll use a very special filter called CI Perspective Correction, which conveniently does exactly what we need. It takes an off-angle rectangle and straightens it. We're now ready to collect sample images of box top logos. These will be necessary to develop and test the detection algorithms, which we'll be covering for the remainder of this talk. To collect samples, we built a sample collector app which uses the exact same techniques we've already covered to detect rectangles, clip them out, and straighten them. We eventually collected over 300 samples of box tops and non-box tops. It's important to test our algorithms against images which might be confused for box tops to make sure that our detector won't interrupt the user unless they're actually trying to scan a real box top. But one big question remained. How can we compare two images to see if they are similar, even if they aren't exactly the same? The answer is called a perceptual hash. It's basically a fingerprinting technique, similar to those used to detect copyright infringement on photo or video sharing websites. Here's how it works. First, we crop the image. We remove about 10% of the image from all four sides. This will remove any variations around the edges of the image due to differences in packaging colors and styles. Next, we convert the image to grayscale. This allows us to ignore a wide range of color variations which aren't important when we're trying to detect if an image contains a box top. Now we normalize the image. This makes the darkest parts of the image completely black, while the lightest parts of the image become completely white. And it's done to account for variations in camera exposure and room brightness. We scale down to a consistent size. This eliminates differences in the sizes of the images and removes some minor details which are unimportant when comparing two images. Then we run the image data through a discrete cosine transform, or DCT. This process is similar to the image compression used in JPEG files and leaves us with a mathematical representation of the major features of the image. An interesting property of the DCT transformation is that all the major details about the image are grouped in the upper left-hand corner. This is the basis of our image fingerprint. Now we need to convert this fingerprint into a number which can be compared to other fingerprints. Each pixel is rounded to either black or white, based on its relationship to the average pixel color in the data. If it's darker than the average, it becomes black. If it's lighter than the average, it becomes white. If we assign a 0 to every black pixel and a 1 to every white pixel, we can now represent this fingerprint as a binary number. I'll save you some work and just tell you that this number is approximately 1.4 quintillion. In fact, there are approximately 18 quintillion possible fingerprints of this size. This is the perceptual hash of the original image. The final step is comparing these hashes to see how similar two images actually are. For this, we'll use a relatively simple mathematical property called the Hamming distance, which is named after mathematician Richard Hamming. To compute the Hamming distance, we simply compare the digits of the binary numbers one at a time and count how many are different. In this case, 3 of the digits are different. Another way to represent this is with the Hamming similarity, which is the percentage of digits which are similar. In this case, 5 out of 8 digits are similar, so we end up with a Hamming similarity of 62.5%. For our use case of detecting box tops, we only want to notify the user if we are very sure that the image contains a box top. So we've set our similarity threshold at 96%. Here you can see some sample images along with their Hamming similarities. Not very similar, nearly identical, and the exact same image compared to itself. Finally, we're ready to pick a good set of target images from our collection of samples. Targets were selected based on how many other samples they were similar to. A high-quality target matches many positive samples with no false positives. Now for a quick recap of the entire process. We detect rectangles. We clip out the rectangle and correct the perspective. We compute the perceptual hash. We compare the hash to the hashes of our target images. If there's a match, our test app will highlight that rectangle with a magenta overlay. And here it is performing that entire process 60 times every second. And finally, here's box top detection integrated into our production app. You'll notice the logo design has been updated since our previous examples, but we're able to detect both types. I'd also like to point out how subtle this user experience is, especially when you compare it to the flashy test apps we've just seen. While we might be tempted to show off this incredibly complex process, it's important to remember why it exists. To work silently in the background and provide just the right amount of helpful feedback if the user needs it. The new Box Tops for Education app, including computer vision-aided box top detection, is available today in the App Store. I invite you to download it and try it out for yourself. I hope this talk has inspired you to look for ways to use these tools in your own projects to build delightful and helpful user experiences. And speaking of delightful experiences, if you're a developer with a passion for solving challenging problems in ways that surprise and delight users, then the people at Livefront would love to talk to you. Find us online at livefront.com/careers. If you have any questions or comments about this talk, get in touch with me at paul@livefront.com. Thanks to the Mini-Star board, staff, and volunteers for putting on this amazing conference, and thank you for watching.